for the words and also for inviting me to come here and speak about this topic, particle Markov chain Monte Carlo. I don't know, do people online hear me as well? I can't really see anyone.
Yes, yeah, it's they're
there on that screen.
Yes, should be, yeah.
Hopefully you can hear me. Right, so I hope that you have some energy now after lunch to listen to one more topic, 3 hours about particle Markov chain model. So this is really sort of a framework which is about making use of particle filters or SMC together with Markov chain model. Specifically to use SMC to construct efficient high-dimensional MCMC kernels or MCMC proposals. So now we're towards the end of this week, and you have learned a lot about SMC, I'm sure. So I can kind of count on that you're now experts on SMC. But I'm also a bit curious to hear how familiar you are with MCMC, since we're going to combine these classes of algorithms. So just for me to know my audience a bit better, hands up if you know what MCMC is. Everyone, maybe keep them up. And then you can lower or keep your hand up if you would be comfortable writing down pseudocode for Metropolis Hastings algorithm. Not everyone, but maybe keep it up if you know what the Hamiltonian Monte Carlo is.
I do actually.
A little bit mixed, but it seems like you have some experience with MCMC, or at least you're familiar with it. So, right. So this tutorial, as all of them, I guess, this week will be split into 2 parts. So the first part will be about one class of particle MCMC methods called particle Metropolis Hastings. So this is a way of using the Metropolis Hastings MH algorithm to parameter inference, Bayesian parameter inference in state space models or other models for that matter, where we can use of SMC to infer some latent states or latent variables. So we can kind of think about this as a way of mimicking an exact Metropolis Hastings algorithm. I will get back to this. And these particle MCMC methods, they have been sort of coined exact approximation methods, or belong to that class of algorithms, which sounds a bit funny, but it's really about trying to mimic some ideal MCMC algorithm that we're not able to implement, but doing so in a way which still allows us to have a consistent MCMC, sort of a valid MCMC method. Right, but I will start by just talking about how we can do Bayesian parameter inference in state space models, because I will derive all the algorithms in that context, to just see what is this that we're aiming for, which is this sort of idealized algorithm that we're trying to approximate. And when I sort of prepared these slides, I wasn't sure exactly what you would cover earlier this week, and then I've been sort of receiving the slides that have been sent out, and I've realized that you've probably seen this picture as many times as the lecture here. But anyway, we'll work with state space models. I will skip through this quite quickly now because I think that you are familiar with it. But we have some latent states X, we have observations Y, and importantly here is that we have some sort of model parameter theta, which governs the state transition and also the observation model. And the task that we're concerned with would mainly be to infer this theta conditionally on some observed Y's. You have also seen examples of such models. One example is the linear Gaussian state space model, in which both the state transition and the observation model are linear Gaussians. And then we can, for instance, have these sort of transition matrices here, and the noise variances as our model parameters. And as you've seen here, I will use this color coding. I don't know how clearly here it is on the slides, but blue means latent states and red means parameters. So just as one example of what could be the parameters that we would like to infer. But more generally, we can also work with nonlinear state space models, where, for instance, we could have this form where we have some additive noise here, but where the state and observation functions are nonlinear. Okay, and yeah, I just had one example of what this might be, but I think you have seen plenty of those examples this week. Right, so one way of representing such a state space model is by using the probability density functions, or the transition densities and observation densities, and we'll work with this formulation throughout the lectures here, which means that we use this symbol little p to denote any conditional probability density that is kind of implicitly defined by the model. We have some transition density here, that's how we move from one state at time t to the next state. One to the next state. We have an observation likelihood, and we have some distribution for the initial state. And as I said, we are interested in inferring the parameters. You can imagine doing that in different ways, either, for instance, using maximum likelihood formalism, where we want to optimize data to maximize the likelihood of the observed data, or we can take a Bayesian approach where we also assume some prior distribution over data, and then we want to do Bayesian parameter inference, so infer the posterior data conditionally on the observed y's, and that is what we're going to focus on now. So with this probabilistic formulation of the state space model, we can also write down sort of the complete joint density for all the variables that appear in this model. So the unknown parameter theta, all the latent states, and all the observations. And using the conditional independence properties, the Markov property of the state space models and so on, it turns out that this joint density over all the variables can be factorized into this way, right? So here we just have some prior distribution over theta. We have some prior over the initial state x0 conditional theta. We have a product over all of these Markov transition kernels, and then we have another product here over all the observations. And we'll kind of think about the model as being this complete joint distribution or joint density over all the variables. And specifically, what we're interested in is computing the posterior, which means replacing this comma here with a conditioning bar. You could say, what is the conditional distribution over theta and the x's conditionally on the y's? Okay, so with this sort of model in place, we'll now turn to Markov chain Monte Carlo as a way of approximately solving this Bayesian inference problem. And to present this in slightly more general terms, we will just assume that we have some target distribution pi of x. To get this one, target distribution pi of x that we're interested in approximating or sampling from, and more specifically, we can think about approximating pi by approximating some expected values of some test function phi here with respect to this distribution pi. That's a typo. Don't worry about that much. Just an expected value with respect to pi. And for instance, if we are now doing this for a state space model, x here could, for instance, be the unknown parameter, and then our target distribution pi would be the posterior distribution theta given the observed y's. But it could also be that we're interested in finding the posterior distribution of both the latent states x and the model parameter theta, and then get this implementation above. This little x here would be both states and parameters, and the target would be the joint posterior over both of those. But for now, I will keep the presentation a bit more general and just talk about, we have some target distribution pi of x that we want to sample from, essentially. So assuming then that this pi of x is not available, typically, we need some way of approximating it. Then how can we, well, two common strategies for this approximate Bayesian inference are variational inference and Markov chain Monte Carlo, where variational inference would mean that we postulate some parametric family of distributions that are now our approximating distributions, and then we try to optimize the approximation sort of within that parametric family to get an approximation that is as close as possible to the true posterior in some sense. Whereas in MCMC, we instead work by simulating some Markov chain, which is constructed in such a way that it admits this target distribution pi of x as a limiting distribution. And just to show you very briefly, going back to my question, it seemed like you're all familiar with MCMC to some degree, at least. But anyway, just to show you the idea, well, it essentially builds on stationarity of stochastic processes. So if I would just take some very simple stochastic process here, this is just a first order autoregressive model with some Gaussian noise. And I simulate this from some initial state, which I just arbitrarily set to -40, then you can see that this quickly converges to some stationary regime here. And specifically, as time goes to infinity, the marginal distribution over the state of this stochastic process will converge to the stationary distribution or limiting distribution. And in MCMC, we're using this type of convergence of a stochastic process to simulate from the distribution of interest, pi of x. And more specifically, you can think about an MCMC algorithm as generating a stochastic process, or more specifically, a Markov chain or Markovian stochastic process. And according to the following step, so we set the initial state of this Markov chain arbitrarily. And then we have a loop where at each iteration, we draw a new value for this stochastic process, the Markov chain, by simulating from some Markov kernel, which I did by kappa here. So this Markov kernel, it's just sort of a conditional distribution of over the next state conditionally on the current state. Now, for this to be useful for actually solving the problem of interest, simulating from this target distribution pi, we have a couple of basic requirements. The first requirement is that this kernel kappa should admit target distribution pi as a stationary distribution. This means that if I would initialize my chain with a sample from pi, then if I apply the kernel once, so if I generate a new sample, that should also marginally be distributed according to pi. Or put differently, if we now want this to converge towards something from pi, in the long run, we should sort of have samples that are distributed approximately according to pi, and then we should remain there, sort of all the marginals thereafter should also be distributed according to pi. And mathematically, that just means that if I consider sort of a joint distribution over some current state x, which is distributed according to pi, and then I move one step with the kernel and I get another state x star here, then marginalizing out the state x here, x star should also be distributed according to pi. And the second basic requirement is really just that this kernel should be such that it allows us to move towards pi. It needs to be able to explore the state space in some way. And more formally, we say that the kernel should be ergodic. So we'll not go into details about this, but essentially you can think about it as it should reach pi from any initial distribution. so that it doesn't get stuck in some subset of the state space. Okay. Now I went through this quite quickly, but are there any questions so far? If there are any questions, feel free to interrupt me at any time. Right, so there are, of course, different ways of constructing such kernels, MCMC kernels, that satisfy both of these requirements. The most famous one is the Metropolis-Hastings algorithm, which is a type of accept-reject method or mechanism, which is such that at each iteration, we propose a new state for the chain by simulating from some proposal kernel here, Q. We get this proposed sample X dash. And then we have an acceptance probability, which is computed according to this expression here. It's essentially the ratio of the target at the proposed sample and the current sample. And then we have the ratio of the proposals, but in the reverse order, you could say. So the proposal of the current sample divided by the proposal evaluated at. And then with this probability alpha, we accept X dash as a new state of the chain and set the next value according to X dash. Otherwise, we remain at where we were. So this is one way of constructing such MCMC kernels, and we will make use of this now for the context of dynamical systems or state space models. Small illustration here. Let it run anyway. This is just showing an application of this Metropolis-Hastings algorithm for a simple two-dimensional problem, which is such that the target distribution is this bimodal Gaussian, and you can see how that chain then starts exploring these two. Okay, so as I want to use this Markov chain to approximate pi, or more specifically approximate expected values with respect to pi. So just a few words about what that actually means. Well, first and foremost is that if we have a Markov chain that satisfies these requirements that we had, then it can be shown that sample averages, if we average some function phi evaluated at the states of this chain, and then we do sort of a temporal averaging over the states of the chain, then this will converge towards the true sort of expected value that we're interested in estimating. So this is how we would actually use the output from the MCMC algorithm for estimating these expected values. And furthermore, if we make some additional requirements on the ergodicity properties of the chain, specifically requiring that it's geometrically ergodic, then it can also be shown that these sample averages, there's sort of a central limit theorem that applies here. So these averages will converge at the Monte Carlo rate of square root of m towards a normal distribution, which has some asymptotic variance. And this asymptotic variance, it happens to be equal to variance of this test function phi at the target distribution. So this factor here is what we would get if we would just apply sort of a vanilla Monte Carlo estimator that would sample IID draws from pi. In the MCMC setting, we get an additional factor here. So we inflate the asymptotic variance, which means that we are doing worse than the ideal Monte Carlo estimator, which makes sense. And how much worse we're doing, well, it depends on this correlation here between consecutive states in the Markov chain, and specifically the integration of this correlation function, and this is something which is referred to as the integrated autocorrelation time. And the reason for why I'm showing you this is that it's something that is commonly used in practice as well. Yeah.
My quick question is there any conditions needed for this infinite series to?
Yeah, it's essentially that you have this type of geometric ergodicity that you.
Okay.
So if the chain is geometrically ergodic, what that means is that it's kind of forgetting its the past state geometrically fast, then you will have a convergence of this series as well. Yeah, so the reason for why I'm showing you this is that it's something that's also very commonly used in practice as a diagnostic tool for analyzing how well an MCMC algorithm is working. And I will show you some plots like this later on, so you know what they mean, sort of. But if the way we are doing this in practice is that we can actually estimate this autocorrelation function of the Markov chain, and we can then plot the autocorrelation function, which is now a function of the lag, and then it shows us how strongly are two states sort of that are separated by a certain lag, how strongly are they correlated. So this is a function that starts at 1 because at lag 0 then it's correlated, and then it typically drops to 0 like this. And the integrated autocorrelation time, that would be the area under this curve. So we want that to be as small as possible. And yeah, if you haven't seen this before, that's essentially what you need to take with you, that whenever you see an autocorrelation plot like this, the more sort of rapid it drops towards 0, the better. Right, so with that sort of background on MCMC, I hope that we are now equipped to see how we can make use of MCMC to solve the parameter inference problem in the state. If you recall from the previous slide here, we said that the full probabilistic model essentially just a joint distribution over all the variables of the state space model, both the unknown theta, all the latent states, and all the observations. And based on this, we want to compute some posterior distribution, which means essentially evaluating the marginal likelihood here, which appears in the expression, which would then amount to integrating out all the latent variables, both the x's and the thetas. So if we now want to target this posterior distribution here using MCMC, because we assume that we will not evaluate this on closed form, so I want to approximate this posterior instead. Then we can just plug that into the Metropolis listings algorithm with theta, with pi now being replaced with this posterior p theta given y. And we construct some proposal kernel here, Q, which allows us to propose a new sort of value for theta, the model parameter, conditionally on the previous one. We work out that the acceptance probability here now will only depend on the prior over theta. This we assume that we can evaluate. And then we have a likelihood term here, which is now the likelihood of the observed data conditionally on the proposed value of theta. And this is now an algorithm that we can run to do parameter inference in this model. But it's important to note here that the acceptance probability in this algorithm depends on this likelihood, so py given theta. It appears in this expression that we had for the acceptance probability. And in order to compute this, we need to marginalize out the states, the x's in the model. So this is something that we can do in some special cases. For instance, in the linear Gaussian state space model, we can run a Kalman filter. The Kalman filter computes as part actually of the time and measurement updates in the Kalman filter, you compute this sort of innovation, which is essentially the posterior mean of the observation and the innovation variance, which is the covariance matrix of this. So based on those quantities, we can multiply all of these predictive likelihoods together, and we get an expression for the the joint likelihood conditionally on some value of theta. So what you would do is that you propose a value for theta, you fix that value, and then you run your Kalman filter, you collect all of these terms here, multiply them together, and then you get the likelihood that you need in order to compute the acceptance probability. As a practical note here is that since we need to run a Kalman filter to compute this quantity likelihood, that's sort of a main part of the computational cost typically for applying this algorithm. It makes sense to store these intermediate quantities so that we don't need to recompute them at each iteration. Well, we need to compute one such likelihood for the proposed value, but if I then accept that proposed value, then I can just store the likelihood that I computed. I will denote that by Z of M. So this is sort of the value that we computed for the likelihood conditionally on theta of M. But it's sort of just a computational trick, you could say. And with that, we obtain an algorithm that looks like this. So I just made some minor modifications here from the one before. So here at step 2b, we now compute, should not be the hats here, but we compute this likelihood and we use that in the expression for the acceptance probability. If I accept this particular draw theta dash, then I both sort of set the next state of the chain according to the proposed theta dash, and I also store the value for the likelihood. Whereas if I reject this proposed sample, then I copy the previous value of the chain, and I also copy the previous likelihood value. Right, but this assumes that we can actually compute this likelihood, right? So what about a general nonlinear state space where Kalman filter is not applicable? Then we can't just apply this algorithm as it is. But we know from earlier in this week that we can run SMC or particle filter to estimate the likelihood in a general nonlinear state space model. So could we then use an estimate of the likelihood in this Metropolis Hastings algorithm and still sort of end up with a valid algorithm? And valid here in the sense that we still want this sort of ergodic theorem to hold. We still want this to converge towards the true posterior distribution in the long run. And this is where particle MCMC and specifically the particle Metropolis Hastings algorithm comes in. So before going into that, I will just briefly recap some things, some properties of the likelihood estimator, that likelihood estimate that we get out from the particle filter, and also introduce some. So by now you know what the particle filter looks like. I will do all the derivations in this lecture with the bootstrap particle filter, but everything that I say about particle MCMC can be generalized to any sort of valid SMC algorithm, you could say. So it's not restricted to this, it's just for convenience. So we look at the bootstrap particle filter. It essentially consists of this sampling, resampling, and weighting steps. So here we initialize by some particles at time 0. And now I have assumed that I don't have any observation at time 0, so I'll just set all the importance weights at time 0 to 1/n. And then in each sort of consecutive time step, we have 3 steps here. We have a resampling step where we draw some ancestor indices from a categorical distribution defined by the weights. This ancestor index ATI tells me which particle at time t minus 1 that particle I at time t comes from. So on that in my transition distribution, I simulate XTI from this, and then I compute weights according to the observation likelihood. These W tildes are unnormalized weights, and then we normalize them to get the W's without the tilde. And running this algorithm does not only provide a solution to the filtering problem, but it can also be used to compute an estimate of the data likelihood, and we get this more or less as a byproduct. And I will call that Z hat, and it is given by this product over all time steps of the sum or the mean of the unnormalized importance weights, the W tildes. I think you have seen this earlier this week as well, Lindsten. Okay, so I said that I want to talk a little bit about the properties of this estimator. And first thing to note is that this estimator is a random variable. And what do I mean by that? Well, essentially, if I run the particle filter multiple times, I have the same data, but I just independently apply the particle filter multiple times, I will get different realizations of all the particles and so on, and I will get different realizations of this likelihood estimator. So we can imagine this as drawing sort of samples from some distribution over the likelihood estimator Z hat. To make that more explicit, we can note that the particle filter makes use of random variables internally in order to initialize, resample, and propagate particles. The weighting step in the particle filter is a deterministic function of the particles. And the likelihood estimator, that's also sort of a deterministic function of the weights. So we can view this likelihood estimator as also being a deterministic function of all the particle positions, all the x's, and all the ancestor indices, the a's. To make this even more explicit, well, we can introduce this notation here, which is the bold x's and the bold a's, and these are simply the collection of all the particles that we generate at time t. So generate n particles, then bold x equals all that collection of all of those n particles. And similarly for the ancestor indices. Then it follows that the distributions of these bold x's and a's, well, we do this conditionally independently at each time step. So when I initialize, I sample n particles independently from this initial distribution. That means that the distribution of the bold x is, or bold x0 is just the product over these initial distributions. Similarly, in the resampling step, if we assume multinomial resampling, as I had in the algorithm, conditionally on the particles from the previous time steps, these ancestor indices are drawn independently from a categorical distribution over 1 to n. So again, we get sort of a product here over all particles, and the distribution of each ancestor index is given by the importance weights. And finally, conditionally on the previous particles and the ancestor indices, we have the propagation step where we again simulate conditionally independently from these transition kernels. And putting all of this together, we can write down what the full joint distribution over all the random variables generated by the particle filter is. And I will denote that by this psi. So it's now a distribution over this high dimensional space, which is the space of all the particles and all the ancestor indices. So the domain here would be, well, if each particle x lives in some calligraphic x here, that space, then we have this Cartesian product here, the n times t plus 1 whole product of x for all the particles at all time steps. And then we have the ancestor indices here. They live in the space 1 to n. They're categorical variables. And then we raise that to n to the t because we have n such ancestor indices at each time step. We get this kind of massive probability distribution over all of the random variables generated by the particle filter. And we can kind of think about executing the particle filter gives me one realization from this high dimensional distribution. So, as I said before, this likelihood estimator is now a deterministic function of these variables, the both x's and a's. So this means that this distribution psi that we have over x and a, it also sort of induces a distribution over z hat. I will use the same notation psi here to denote that as well. But this is now sort of much reduced distribution in some sense. In particular, this is now a distribution over the positive real line, because the estimate of the likelihood, that's a real number, and it's a non-negative real number by construction because all the weights are positive. So we get some sort of induced distribution over the positive real line. And again, running the particle filter once, computing this likelihood estimator can be thought of as generating one sample from this. I don't know really what it is. I can't write down a PDF for this because that would involve integrating out all the random variables, all the x's and the a's from this complicated distribution that we had on the previous slide, but I can simulate from it by just running the algorithm.
I think it's past 15. We have another plug there.
Out of that. Okay, final thing to note here about this likelihood estimator is that it's unbiased, and I think that this is something that you have encountered before. And what I mean by that is simply that the expected value of this z hat with respect to the distribution psi is such that, well, it's equal to the true likelihood. And this holds for any number of particles. So a non-asymptotic result. We don't have to rely on running it with a large number of particles for this to hold. And it also holds for any SMC algorithm, as I said before, so not just the bootstrap. And this unbiasedness is a property that we will use for constructing this particle Metropolis-Hastings method. Okay, just as an illustration here of what this means, the unbiasedness and the randomness of this estimator, if we consider a simple linear Gaussian state space model here, this is simple enough so that I can actually compute the exact likelihood using a Kalman filter, as I said before. But I can also apply a particle filter to this just to test sort of the properties of this likelihood estimator. Worth to note here is that we only have 20 measurements. It's a one-dimensional, very simple linear Gaussian system, so it's not a very complicated problem. And if I then apply a bootstrap particle filter with 100 particles, I do that 10,000 times and collect all the likelihood estimators, and I can plot the histogram over those estimators. It looks something like this. So we can indeed sort of confirm or supports this claim that I had that it's an unbiased estimate, because if I look at the mean here, it's, well, looking at the mean of the ratio here between the estimator and the true value, it's very close to 1. But we can also see that there's a fair bit of spread here in this histogram. So even in this simple case, we can get likelihood values that are twice sort of factor 2 off with fairly high probabilities. Just as an observation. Okay, with this, we're now ready to derive this particle Metropolis-Hastings algorithm. And going back to what I showed you before about doing exact Metropolis-Hastings for a linear Gaussian state space model where we could evaluate the likelihood using a Kalman filter, the algorithm looks like this. So what we're going to do now is just to replace the Kalman filter with a particle filter. So it looks very similar. Flipping a bit back and forth here, we see that in the Kalman filter, we initialize on theta 1, we compute the likelihood, Z1. Now we will instead run a particle filter to estimate Z1. Similarly, here in step 2b, we compute the likelihood using a Kalman filter. I will replace that by running a particle filter and then computing this estimate, which we can think about generating a sample from this distribution psi. Kind of propose a value for theta, I condition or kind of parameterize my model using this theta dash. I run the particle filter and then I propose a value for the likelihood, you could say. And then apart from that, well, the algorithm looks exactly the same. So we get the same acceptance probability, but true likelihood is now replaced by the estimate. If we accept, then we accept both the theta and the likelihood estimate. And if we reject, we kind of copy the previous values that we had. And that's sort of an important distinction here still, that even though the algorithms look very similar, in the Kalman filter, well, we compute this likelihood at each iteration, and then I said we can store it in this variable Z just to for computational efficiency. But the state of the Markov chain is really just theta, because the likelihood is a deterministic function that we can compute based on theta. Whereas in, messed up the transitions here, I see. So, whereas in the particle metropolis Hastings algorithm, this Z hat is now a stochastic variable, and it should be viewed as part of the Markov chain. So we need to sort of keep track of this along with the thetas. And if I accept a value for theta, I also accept its sort of corresponding likelihood estimator. So it's really a Markov chain now on the pairs of thetas and Z hats. And as we will see when I sort of derive why or show you why this is actually valid with it, turns out that we need this likelihood estimator to be both non-negative and unbiased for this to work out. And whenever you sort of run a metropolis Hastings algorithm where you replace some likelihood with a non-negative and unbiased estimate of that, that's sort of a general family of methods called pseudo-marginal methods. So the particle metropolis Hastings algorithm is one example of this, but there are other examples as well. And they're all sort of based on the same derivation that we'll have a look at next. And to show you why this makes sense, how we can actually come up with such a pseudo-marginal method, we will make use of auxiliary variables. Is that something that you have come across before, this term, auxiliary variable? So, well, it's a trick that is very commonly used when working with Monte Carlo methods. Pseudo-marginal methods is one example of this, but there are many examples of sort of sophisticated MCMC procedures and other Monte Carlo methods that are different ways of making use of auxiliary variables to construct some method. And the idea is really just that if we have some target distribution pi of x that I want to sample from, and it turns out to be difficult for some reason to construct an efficient MCMC algorithm or other Monte Carlo method for that reason directly for pi of x, then I will introduce some other variable u, which I refer to as an auxiliary variable. I will do this in such a way that the joint distribution pi of x comma u admits the original target pi of x as a marginal. And specifically, that will always be the case if we construct this directly in terms of some conditional distribution over u given x, and then I define the joint as simply the product of the original target and this conditional. But that's not really strictly necessary, and any way in which I can construct such a joint distribution over x and u such that the marginal of the x coordinate coincides with the original target of interest, then I can target this joint distribution, which I will refer to as an extended target, using my Monte Carlo method instead. And if I can then sample pi of x comma u, then I can just throw away the u samples, and I'm left with samples that target the corresponding marginal, which by construction was the original target of interest. In some situations, you have sort of some insight into your model that there are some hidden variables, latent variables that we can use as auxiliary variables to expand the model in some way, expand the target. The state space model is one such case. If I start by just saying that my target distribution is the posterior of theta given y, then I could introduce the latent states as auxiliary variables and target the joint posterior x and theta given y. Even if I'm really just interested in solving the parameter inference problem, maybe that sort of helps me to construct a good algorithm. But this is not necessary, so we can also introduce some completely artificial auxiliary variables as long as we satisfy this condition of having the marginal of the joint being equal to the target of interest. And specifically, if we now do this with an MCMC algorithm, I will construct an MCMC procedure that targets the joint over x and u. This procedure will give me a Markov chain over the pair x and u, right? And as I said before, if I'm only interested in the x coordinate here, then when I'm done, I can just throw away the u variables, and then the x's here can be used to approximate expectations under pi of x. Now, the u variables are typically used internally in the algorithm, so we can't throw them away until we're done, but sort of when we have finished some. This derivation. So with this idea now with auxiliary variables, we'll see how we can come up with this pseudo-marginal approach, and the particle metropolis Hastings as one example of this. So the target distribution that we have is now pi theta, which we name for this posterior distribution over theta given the data y1. And by this rule, we can write this as prior times likelihood divided by this marginal likelihood. And as we said, the likelihood here is intractable. So but we know that we have access to this unbiased estimate of it. We can write this likelihood, an intractable term, y1 to t given theta, as an expected value with respect to this psi distribution. Distribution sort of defined or induced by the particle filter of z hat. I'm just writing this out as an integral. We get the integral over z hat psi z hat. All this expression that we have for the target, just store here, then plugging this into posterior, we get our target by theta. And I just take the other factors here and push them sort of into the integral as well. Right, this is an integral over z hat sine z hat given theta times theta divided by y1 to 2. And this thing here now looks like marginalization, or we can at least think about it in that way. So some distribution here, which is the integral over some other thing here. So if I just define this, I of theta comma z hat. Then what we have here is the marginalization integral, this joint distribution over theta and z hat, and marginalize out the z hat variable. And this gives me back pi of theta. So this could be valid if I'm going to be able to interpret this thing now as a probability density function over this parent theta and z hat. I need this to be non-negative. I need it to integrate to 1. Well, non-negativeness I get if I know that my likelihood estimator here is non-negative. All these factors here will be non-negative. And unbiasedness tells me that, well, if I integrate this from the derivation that we here, integrate it first with respect to z hat, then I get back the original target. If I then integrate with respect to pi, then this is, that is a probability density. So then that will also integrate. We can view this as a joint distribution. And this is now what we will use as the extended target distribution for the pseudo Markov. Make sense?
I have a potential.
Yeah.
Data.
Yeah. I guess it's sort of a question about whether or not you're Bayesian at heart. But this is sort of the Bayesian approach to doing parameter inference, that you want to actually find the full posterior distribution over the parameters. It could be either that you do this because you want to compute some posterior mean, but also maybe you want to represent the uncertainty, your sort of ignorance about the parameters. So, I can mention that now I'm presenting these algorithms as doing Bayesian inference, and that's sort of where they come from, but particle MCMC can also be used for doing maximum likelihood based inference, like point inference. And I will not go into the details of that. Okay, so with this construction, we now treat this z hat as an auxiliary variable. We define this extended target distribution, which we have shown has the correct marginal over the theta coordinate. So the pseudo marginal method is really just a standard MCMC procedure for targeting this joint extended target. And if we're now going to define or construct an MCMC procedure, well, we have target, and I'm going to work within the Metropolis Hastings framework for now. So next thing would be to define some proposal distribution. And this should now be a proposal distribution over the pair theta and z hat. But here we need to think a bit about how we're actually going to implement this, because, well, we have this extended target, but we really gained anything so far, because we have now got the target distribution, which I can't even evaluate pointwise, because this psi density here, that I can sample from this easily by just running the particle filter, but I can't evaluate this PDF pointwise. And in the Metropolis Hastings algorithm, we typically need to evaluate the target. So is this a problem, right? But in order to circumvent this issue, we'll make use of the freedom in constructing the proposal so that we get the cancellation of these intractable terms. So we will use this psi also as part of the proposal distribution. In the Metropolis Hastings acceptance ratio, you have this, or the acceptance probability, you have this ratio between target and proposal. If we can then get the cancellation of the intractable terms, we're good to go. So the pseudo-marginal method, and as I said, particle Metropolis Hastings is an instance of this. It's both using this extended target and also using a particular choice of proposal for making this tractable. Specifically, we will use now a joint proposal for the pair theta and z hat, which factorizes in this way. So we assume that there exists some kind of proposal only over the theta coordinate. This is the same as we had in the ideal situation, that we need a proposal for the theta variable. So here we can select something arbitrarily, but then conditionally on the proposed draw theta dash, we propose z hat according to this distribution psi. And what that means in practice is that we first propose a value of theta, we then take this, parameterize our model using theta dash, and we run the particle filter and return the likelihood estimator. And we have generated a sample from this joint proposal. And if we then just take this and plug it into the Metropolis Hastings acceptance probability, well, as I've already mentioned, we'll get some nice cancellations. So just to verify that, here is the standard Metropolis Hastings ratio, where we have the joint target and the joint proposal. In here, just expanding all of those terms, we get something which looks a bit messy here, but this is just how we define the extended target. So that's the first factor over here. Here we have the extended target again. The inverse of that corresponds to this here. And then over here we have the ratio of the proposal distributions according to the definition above. And looking at this, we see that, well, first of all, the marginal likelihood cancels. That's nice. That's something that we usually have when working with Metropolis Hastings, right? That you have an intractable marginal likelihood that cancels in the acceptance rate ratio. But we also get this cancellation of all the psi. So there are 4 different psi's here. And if you look at this detail, you'll see that they will exactly cancel. And what we're left with is this expression down here. And this is precisely what I had in the algorithm before. So just showing you the same algorithm again. This is what it looks like. So this algorithm, pseudo-marginal method, it's one example of referred to as an exact approximation. And it sounds a bit funny, as I said before, but the meaning is really that it looks, if you just look at the algorithm, it looks like an approximation of the ideal Metropolis Hastings algorithm. Just take this intractable term and replace it with an estimate. But despite doing so, relying on the these properties, unbiasedness and non-negativeness of the likelihood estimator, we can show that it's still a valid MCMC targeting the correct distribution. But there's of course no free lunch, so there is a price to pay for this approximation, and that is that the mixing speed of the algorithm can be actually much worse than ideal sort of counterpart, because we will get sort of a contribution to the acceptance probability here of the Markov-Hastings algorithm, which comes from this Z hat. We have poor estimate Z hat that can sort of negatively influence the acceptance probability, so that we accept much fewer samples than we would have with the ideal sampler. Okay, now I showed you this as just targeting posterior over the thetas. I mentioned in the beginning that we can also use these algorithms for sampling x's, states. Typically, we can target the joint posterior over theta and x. And if we want to get sort of estimates of the latent states out of this algorithm, we can do that by simply selecting one of the trajectories that we generate in the particle filter in step 2b. So that's where we run the particle filter. When we're sort of done with this, or sort of when we have run this particle filter up until time t, we sample one index with probabilities given by the final importance weights, and then we trace the trajectory of that particle all the way back to time 0. And if we then take this trajectory as also part of the Markov chain, then it can be shown that this, together with theta, will target the joint posterior over theta x. I will actually go or get back to this a bit more in the second part of the lecture. Questions about this algorithm?
Regarding the smoothing interpretation, does that require resampling to be disabled?
No, you resample still. So what you do is that you pick one particle at the end, you could say. You pick it stochastically with probabilities given by the final importance weights, and then you trace the genealogy of that particle.
As in through its resampled indices. Yeah. Okay. So potentially it could lead to the recovered distribution, having say like a common ancestor for like the first part of the trajectory.
Yeah, exactly. But then also, since we do this within the context of MCMC, you would get just take one sort of and trace that, then you get one trajectory at each iteration of the MCMC algorithm, which is likely unique because each one comes from sort of a separate run of the particle. But it's of course in some sense an expensive way of doing smoothing, because you need to run one particle filter for each trajectory that you get out. But it's nice because you have sort of statistical guarantees that you're converging towards the correct distribution, despite the fact that you use a finite number of particles. So you kind of rely on the convergence of the MCMC instead. I had a couple of examples here, but I'll skip them. I don't say very much more than that. They are sort of examples of applications where this method has been used. So and this example here is coming from applying it to computer graphics and rendering, and it's an example of where we kind of apply the same ID to something which goes beyond the state-space model. So I mentioned that at the beginning, that I'm deriving everything here now for a bootstrap particle filter and a state-space model, but it's more general than that. Whenever you can apply SMC, you can also turn that SMC into an MCMC kernel in this way. So summarizing this first part, particle MCMC, and think about it as a systematic way of combining SMC and MCC, and more specifically of using SMC within the context of C. It builds on this extended target construction, and you can think about it as applying standard MCMC algorithms on sort of a non-standard target distribution. We'll see that more clearly when we talk about particle Gibbs in the next lecture, which is just applying Gibbs sampling essentially to the same target distribution. This extended target is constructed in such a way that it admits this joint posterior distribution, marginal. Well, I should say maybe a slightly different version of the extended target that we'll look at in the next as well. But it means that we can use these algorithms both for state and parameter inference. And as I said, it's sort of a valid MCMC for any number of particles, but the number of particles can have a impact on the mixing speed of the algorithm. Okay, so I think I had a few more slides here on this part, but I think that I will maybe take the remaining few minutes before the coffee break to start the second part instead. I think there might be a few more slides there. So yeah, but questions?
How expensive computationally is it?
Yeah, I mean, it's the particle filter is roughly linear in the number of particles. Observation there for the resampling step, depending on how you implement that. But it's like linear in n, and then it's linear in the number of MCMC steps. So m times m, n would be the complexity of it. And then the question is how, say that it's valid for any n, how large does it have to be in practice? Well, difficult to say, but it's, you still need to sort of have an SMC implementation that is not completely just collapsing. So you need to have a reasonable number of particles, and in principle you can, well, maybe I can actually get this because it relates to your question as well. So I have a few more slides here, which is about just the properties of the likelihood estimator. And for understanding these this algorithms, it really relies on this likelihood estimator. It can be instructive to also analyze the properties of this thing. And one sort of way of doing that is to look at the central limit theorem also for Z hat, which can be established. And it turns out that this this likelihood estimator will sort of converge to a normal distribution in this way. And if we assume some quite restrictive, but still sort of not completely unreasonable forgetting properties on the state space model itself, it can be shown that this the variance in this likelihood ratio here is roughly some constant c and then t over n. This suggests that n should at least be the same order as t for this to work.
I have a question online.
Yep.
Oh yeah, thanks. Just about when you said it's useful both for parameter and state inference, that by that you mean also joint state and parameter inference simultaneously.
Yeah, exactly. And I should maybe clarify then that it's really smoothing that we solve with this. It's not an online algorithm, so we don't solve the filtering problem, but we do joint state and parameter inference. But you can, of course, use it if you don't have any unknown parameters and apply the same algorithm, then it can be used as a pure smoothing method.
Right.
That just simulates the x's at each iteration. Then it's like an MCMC approach to smoothing.
Thanks.
Yep.
Usually with MCMC, you have like this acceptance value where you have like some theoretical bounds or some theoretical optimum you want to stay close to. Is there also something like this in particle MCMC? And to go further, usually when you try then to hit your acceptance rate or you adjust your proposal, but here your proposal is also your particle filter, so the adjustment is quite hard, I guess. How would you do it on this PMC setting?
So first question about target acceptance rate, you're referring to these like rules of thumb that you want to have a 0.234 acceptance rate. There are similar rules of thumbs for pseudo-marginal methods as well. But they all depend on the assumptions, as always, right? They depend on the assumptions that you make when proving these, deriving these optimal values. There are a few papers. I'm not so sort of certain about the details there, so maybe I shouldn't go into too much. But I think that there were a few papers some time ago where they tried to derive optimal values, and where kind of different groups came up with different rules of thumbs that were quite different. But in general, I think that the you want to have a slightly lower acceptance rate, because you're usually I'll leave that answered. But there are some work on it. And sorry, your second question was
Yeah, the second question is basically MCMC see how to adjust the proposal to increase your acceptance rate or decrease it. Here your particle filter is involved in the proposal. So it's highly non-trivial how to adjust it. And there's like any systematic way.
yeah. I mean, there are two different parts that contribute to the acceptance rate, because we have the proposal looking like this, right? So both the Q and the psi here will affect on the acceptance rate. And we can kind of control them in similar ways to, well, for the Q part at least, similar way to a standard MCMC, that you can reduce or increase the stepwise in some way. For psi, it's really about improving your particle filter estimate. So increasing the number of particles will have a direct influence on the psi part here. And yeah, I mean, in the limit, if you take very many particles, then this will, Z hats in this expression down here will be pretty much the same. So it will be constant, and then you can just remove this and we recover the ideal Metropolis Hastings algorithms.
We have 2 questions online.
Yeah.
Yeah, can you hear me?
Yeah.
Okay. I just wanted to know if there are some variation of this particle MCMC algorithm to be done online. So to modify the estimates of the parameters as new data come.
Yeah, there is maybe the closest thing, at least that comes to mind now, is an algorithm which is called SMC square, where you essentially, if this is now taking SMC and using that within MCMC, you can also take SMC and using that within another SMC, which is doing kind of recursive parameter inference. So you have an SMC algorithm targeting the theta coordinates as well. So that can be done, and it can be sort of shown that it's kind of a valid method using the same tricks as here. It's not really online because you still need to keep track of the likelihoods that are depend on the complete history. So recursive, but not online in the sense that you have a fixed computational cost as t grows.
Okay, thank you.
Yeah, I've got a question, naive question about the smoothing and how you are just picking just one of sort of the particle traces. Is there any advantage to retaining a large set of those rather than just picking one? Or do you get anything, say, by just averaging over the weights, and I guess maybe give you a really good expected value of what the states are?
Yep. You can definitely do that. And the reason really for why I said that you picked one is that the way you show the validity of this approach is by introducing another sort of auxiliary variable which picks out one sample and so on. But then you can do this averaging of all the particles, and that would correspond to doing an analytic marginalization over that additional auxiliary variable, so effectively a Raoul equalization. So that typically reduces the Monte Carlo variance. But in practice, it depends on how degenerate your particle filter is. Going back to the previous question here, that if you're in a situation where all of your particles kind of collapse into a common ancestor after you just go a few steps back, then you don't gain that much from averaging over all of them. But yeah, it's something that you can also do more or less for free. So I would also advise doing it if you actually want to use this for smoothing.
Okay, thanks.
Okay, do we have any more questions? Maybe a question from me then. So according to schedule, we have 10 more minutes until coffee break. Do you want to have a coffee break now and then start a bit earlier, or do you want to go for 10 minutes and then refreshments after that?
When we're having the coffee break now mean that we finish earlier?
Probably not.
Make a vote.
No, democracy. Maybe someone just.
Someone must take a vote and someone must take.